Hello, my name is Richard Kayabyab. This is my project for Machine Learning Foundations for Product Managers from Duke University. My task was to build a model that predicts the net electrical energy output of a combined cycle power plant using a dataset of 9,568 hourly sensor readings and building entirely in Microsoft Excel. In the next few slides, I'll walk through the 5 required steps: identifying the problem, selecting features and algorithms, splitting the data, comparing models, and evaluating the final model. First, the problem type. Look at the PE column. The values are continuous numbers around 443 to 488 megawatts. Because we are predicting a continuous quantity from labeled examples, this is a supervised regression problem, not classification. To measure accuracy, my primary metric is RMSE, root mean squared error. You can see it here on the right, 4.56 megawatts. RMSE is the same units as PE, so it is directly interpretable. Our predictions are, on average, about 4.5 megawatts away from the true value. I also track R squared and MAE as supporting metrics. For features, I use all 4 ambient variables. You can see them in columns A through D. Temperature, exhaust vacuum, ambient pressure, and relative humidity. Temperature and vacuum have the strongest correlation with output, but all 4 contribute. The algorithm is multiple linear regression. Notice the formula bar at the top. Predicted PE equals an intercept plus a coefficient times each feature. In Excel, I compute those coefficients with the linest function. The predicted PE column applies that equation, and the residual column is simply actual minus predicted, how far each prediction is. Model 2 keeps the same algorithm but adds polynomial features. In addition to the 4 originals, I created squared terms, AT squared, V squared, and so on, plus an interaction term, AT times RH. You can see these extra columns highlighted here in columns E to I. Why? A straight line can't capture curved relationships. The squared terms let the model bend to fit the real physics of the plant. Each was made with a simple Excel formula. For example, AT squared is just the AT cell raised to the power of 2. The payoff is on the right. Validation RMSE drops to 4.43 megawatts, and R squared tries to zero or rises to 0.935. Model 2 beats the linear baseline on every metric. Model 3 is ridge regression, a regularized version of the polynomial model. It uses 6 features, shown in the coefficient table here on the left. Ridge adds a penalty on the size of the coefficients. Instead of minimizing only the squared error, it minimizes the squared error plus lambda times the sum of squared coefficient. Here, lambda is set to 1. You can see the loss broken down on the right. The sum of squared errors, the penalty terms, and the total loss. This penalty discourages over large coefficients and helps prevent overfitting. I want to highlight one thing here. When I first reviewed this model, its predictions were wildly wrong, in the thousands of megawatts. On investigation, the prediction formula referenced the wrong column, a centered pressure variable instead of the raw one, and the coefficients were incorrect. I corrected both, as I noted here at the bottom. And the model now produces a sensible training RMSE of 4.38 megawatts. Let me step back to explain how the data was divided. This underpins everything in the previous slides. I split the 9,500 rows into 3 independent sets. 64%, about 6,000 rows for training, used to fit the coefficients. 16% for validation, used to compare the models you just saw, and 20% locked away as a test set used only once at the very end. The golden rule is that a model must be judged on data it has never seen. My validation strategy is a fixed validation set rather than cross-validation, because with this many rows, a single split is already stable and reliable. Now the comparison that drives model selection. This table shows all 3 models side by side, judged only by the validation set, never the test set. Reading across Model 1, the linear baseline has a validation RMSE of 4.66. Model 3, the ridge model, improves to 4.54, and Model 2, the polynomial model, is best at 4.43, with the highest R squared and the lowest MAE. Model 2 wins across all 3 metrics. So my final model is Model 2, the polynomial multiple linear regression. The green row at the banner at the bottom marks that selection. Finally, step 5, the honest test. I take the winning model, Model 2, and apply it once to the 1,914 test rows that were held out from the very beginning. The results: a test RMSE of 4.47 megawatts, R squared of 0.934, and MAE of 3.56. The key insight is that these almost exactly match the validation numbers. The validation RMSE was 4.43, test is 4.47. That close agreement tells us that the model was not overfit and the selection process was sound.